suppose we connect a pure inductor having a self-inductance L and zero resistance to an AC source, as in this diagram A. The potential V of point A with respect to point B is given by V equals L di by dt. And we have that L di by dt is V cosine Wt, okay? So that's the voltage across here obviously is equal to the source voltage. That's the source voltage. Using this, we see that the the current is defined in terms of the current, so we can manipulate this, which is what we'll do just to show how we can get the current here. So we multiply out by dt, that gives us this, and then of course we've got a little bit of I, a little bit of t on there. We can sum both sides up to give us the total I. So if we integrate both sides, obviously that integrating that will become I, integrating 1 will become I, and integrating this we get VW sine Wt add constant. That's the integral of this. And to find the constant, the current is 0 at time equals 0, then the constant obviously is 0. It's just simply IV WL sine Wt. So that's the current. We've got the current and we've got the voltage now. Voltage and current are a cycle out of phase, but this time the voltage leads the current by 90 degrees. This may also be seen by rewriting equation 2 using the trigger density cosine A minus 90 equals sine A. So if you use this trigger density here, you can rewrite this as this. So you can see that the current, like the voltage here, that's the voltage. Current is simply the equivalent to the voltage minus 90 degrees. So the voltage minus 90 degrees is that current. You can see that there's this 90 degrees difference between them. I V WL cosine Wt minus 90, this result and the phasor diagram of here, we can see this phasor diagram, show that the voltage can be viewed as a cosine function with a head start of 90. It's in front, so the voltage is leading the current in this case. In figure B, the points of maximum voltage correspond on the graphs to points of maximum steepness of the current curve, and the points of zero voltage correspond to points where the current curve levels off at its maximum and minimum values. You can see that, I've just shown that here. So the maximum current here is when the voltage is changing at its maximum rate, and when the voltage levels off, the current is changing at its maximum rate. And here current levels off when the voltage is passing through zero and changing at its maximum rate. From equations 2 and 3, the maximum current, again, we can see that the maximum current is going to be when I equals V over WL. You can see with I, for example, when we have this whole angle is equal to 0, then we end up with cosine equals to 1. So we end up with the maximum value is V over WL. Again, we can define the inductive reactance XL of inductor as WL, and this could be measured in ohms. So then we can write I equals V over XL. So the reactance of an inductor is directly proportional to both its inductance L and to the angular frequency omega. The greater the inductance, the higher the frequency, the larger the reactance. So with this, we can see that if we have a very large inductance, then we're gonna have a very large reactance. If we have a very large frequency, we're also going to have a very large reactance. The graph that we're going to show here summarizes the variation with frequency of the resistance of a resistor and the reactance of an inductor and a capacitor. So we've got this line here, obviously the resistance is fixed. It's no dependence to frequency change on the resistor, so that's just a straight line. Now, from this diagram then, as the frequency decreases, so as the frequency gets less and less, the inductive reactance approaches 0 and the capacitive reactance approaches infinity. You can see here. So for a very low frequency, we get very high capacitive reactance. The limiting case of 0 frequency corresponds to a DC circuit. So when there's no oscillations at all, then basically we've got we got a DC circuit. That covers AC resistance, inductance and capacitance.